everybody. Today we have the pleasure to have Mark Hunt from Laboratory of Neuroinformatics at the Biomedycznej Institute of Experimental Biology. So it's a Laboratory of Neuroinformatics, but in fact Mark is doing experimental work, and for many years he is investigating mechanisms of high-frequency oscillations. And today he will give us a presentation about this. So, please go ahead.
So, dzień dobry. Ja będę mówił po angielsku, okay? I think you'll understand better if I speak in English. Right. So the talk is finding the sources of abnormal high-frequency local field potential oscillations, and we're talking about very high frequency, so typically above the classical gamma range, and the effects of ketamine on this type of activity. So, have you heard of ketamine? Has everybody heard of this drug, ketamine? It's a drug that's it's used. It's a drug of abuse. It's currently used as a potential treatment for depression, and it's also has been used for about 60 years to model certain aspects of schizophrenia. Okay, so it's a drug with very diverse human applications, let's say. But you can trace back the work on this drug back to the 1940s, and there was a study done by two clinicians, and they were looking at the effects of anaesthetics in hospitals. And what they found was that there was a surprisingly high death rate, which was produced by the anaesthetics that were administered to patients undergoing surgery in the 1948 to 1952. And what they found was that that they actually said in their paper that anaesthesia may be likened to a disease that could affect 8 million people in the United States. Basically, anaesthesia was quite a high risk when you were in the 1940s and 1950s and you were going to undergo an operation. The death rate in the 1940s was about 1 in 1,500, compared to today, where it's about 1 in 200,000. And basically, the anaesthetics that were used then were not very safe. As you can see, they caused respiratory depression, they caused all sorts of very serious side effects. And so this represented quite a good target for drug companies to try and identify drugs that might be used as anaesthetics in place of what was then the commonplace type of anaesthesia. So there was a drug company in the 1950s called Park Davis, and they were the first company to develop what they believed to be a very safe, a very effective, short-lasting anaesthetic called phencyclidine. It was also, they were so convinced it was a good drug, they gave it the trademark Sernil, meaning serenity, because it seemed to produce a sleep-like, a comfortable, a peaceful-like state in experimental animals. As we said, it was developed in the 1950s. However, when they first administered this to patients, there was quite a severe and unexpected what's called emergence reaction, and this is when a patient recovers from anaesthesia. They started to almost hallucinate, they had bizarre thoughts, they became very violent, and so of course this type of drug was not suitable as a good replacement for the then used anaesthetics. A lot of these early studies were conducted by a group of people, and one of the pioneers was this person, Elliot Luby. He was one of the clinicians that gave patients phencyclidine in the first place. And at low doses, he was a psychiatrist as well, and at low doses he observed that there was symptoms produced by this drug that were very similar to some of the core symptoms of schizophrenia. And he stated in his paper there was impressive similarity to certain primary symptoms of schizophrenia. This includes depersonalization. There's certain psychiatric terms, loose associations. They could not communicate in a way that a normal person would understand or communicate. There was feelings of unreality, feelings of detachment. I've got examples later that can explain some of these terms, but there was a key parallel between what this drug was doing and some of the fundamental features of schizophrenia. If they gave this, they actually did this in the 1950s, they actually gave this drug to schizophrenic patients that were stabilised, and it actually it re-induced their symptoms. They were stabilised patients, so it re-induced their symptoms for 4 to 6 weeks. It was quite surprising, but that's what actually they did, and that was the data that they got. So clearly there's some interaction between this drug, phencyclidine, and schizophrenia, let's say. The drug's no longer used. It is a drug that has been abused in the 1970s, 1980s. It was a drug called angel dust. People enjoyed taking it because it produced these altered states of consciousness and abnormal states of detachment, out-of-body experiences, this sort of thing. But it's clinically not used at all. You don't give this clinically. However, the same company, Park Davis, wanted to continue developing drugs like this, but which were safer and which would try and almost devoid of these side effects, because the anaesthetic effects were quite useful. They didn't produce respiratory depression, and so they synthesised this drug called ketamine, which is the main purpose of the talk. The first human trial was done as well in the 1960s. This person, Edward Domino, he's somebody that's quite a pioneer in the ketamine field, and he's somebody, it's quite amazing, he's still got his lab, he's in the 90s, he still publishes, he still carries out research in the United States. He's still so active in this field. He's like the father of the ketamine field. That's how a lot of people see this. Today, ketamine can be used. It's a drug that does produce side effects in adult patients, but it can be used for some types of paediatric surgery, because children seem to be more resistant to some of the side effects. But it is rarely used. You don't normally use this for humans. Veterinary medicine is quite a common anaesthetic, and experimental animals, it's quite commonly used that people will use ketamine in a mixture with ketamine and xylazine or other drugs. But in humans, you try to avoid giving this if you can. This is because low doses produce something similar to phencyclidine. This is a semi partial schizophrenic state, abnormal thoughts, delusions of reference. I'll show you in the next slide what I mean by these things. The drug also reinstates psychosis in schizophrenic patients. So these are schizophrenic patients that are treated with antipsychotics. They don't have clear psychotic symptoms, but when they're exposed to this drug, it can reinduce the specific types of hallucinations that the patient has experienced in their disease. For example, in this study that's referenced here, there was a patient that believed they had saved the president from some sort of attack, some terrorist attack. He'd stopped an assassination, this is what he believed. He was stabilised and he got given low dose of this ketamine, and this same specific type of delusion recurred in this patient. So there's clearly some interaction between these types of drugs and the schizophrenia-like process. You can actually quantify this. This is a clinical study. This is a baseline. So this is the brief psychiatric rating scale. So it's a scale that psychiatrists use to assess how psychotic-like a person is. And immediately after giving ketamine, there's 2 doses, a low dose and a medium dose. Shortly after giving ketamine, you see quite a significant increase in the psychotic-like symptoms. It's short-lasting. It lasts for about an hour in patients, and then state returns back to normal. And on the right-hand side, you've got what happens in schizophrenic patients. So you've got an increase as well, and it's in these psychotic-like symptoms, and then it returns to baseline about an hour later. And these are in schizophrenic patients that got a saline injection or got a placebo, and their psychiatric rating scale is still at a relatively high level at 8, and that's compared to that state 8. So these are in schizophrenic patients. So there was a lot of research which was done on ketamine and PCP and drugs like this, and it was found that one of the key receptors that these drugs act on are NMDA receptors, and there has been a lot of work done there's a lot of evidence that suggests that NMDA receptor hypofunction, abnormal functioning of these receptors, is involved actually in schizophrenia. So there's a good link between NMDA hypofunction, and schizophrenia. I'm just going to show you a couple of well, 4 quotes of what people feel like when they're on ketamine. So in this case, it's a normal person given ketamine. They felt that people were acting like they're in a movie, a very strong feeling that they're perceiving an imitation of reality, like they're watching a documentary or watching TV. Nothing seems real. This is this, in a sense, depersonalisation. They believe that, another patient reported, there were thoughts that were happening that I wouldn't normally think about, and it just seems like someone else was putting them there. This is like a type of delusional experience. This is quite a long quote, I'm not sure. You can. I'm cautious of the time. I don't want to spend too much time reading this because I want to get to the core of the results. But the point is that ketamine and PCP produce abnormal states of consciousness, abnormal thought processes that parallel certain of the key features of schizophrenia. That's all I really want to say. As I've said in that last slide, this is just to reiterate, ketamine produces NMDA receptor blockade. This is one of the key features that's believed to be important in this drug and also PCP. An endogenous NMDA receptor hypofunction may contribute to schizophrenia. So in our experiments, the rationale is that blockade of NMDA receptors may influence neural networks that are involved in psychosis. That's the fundamental rationale for the experiments. And if we can understand how NMDA receptor antagonists produce their effects in rodents, we might be able to understand some of the networks that are involved in psychoses, and perhaps even in a complex disease like schizophrenia. I should finish at 12, is that right? Or just before? Or 12? 12, okay. So now I'm going to talk about the data, because I think that's probably what's the most interesting. In the lab, so for the last, I don't know, 15 years, maybe, something like that, I've been recording local field potentials. So are you familiar with what a local field potential is? So you put an electrode in the brain. This is the rat brain. In this case, it's targeted at the nucleus accumbens, the shell structure, the shell of the nucleus accumbens. You record the local field potential, which looks like this. Then you can filter it and extract different components of the oscillatory frequencies. Normally, you can see quite marked delta, theta. Sometimes you can see bursts of gamma activity. But in particular, in this high frequency band, 130 to 180, you don't normally see much. In a normal state, in this part of the brain, you don't see much. In hippocampus, it's a different story. You see sharp wave ripples and this sort of thing. But here, you don't really see very much activity. So this is another example of a recording from the accumbens. The raw signal and the high frequency oscillation. There's not much there. The power spectra, which I'm sure you're familiar with. The red bands, the red lines, just indicate this high frequency range. And you can see there's not much happening. But as soon as we give the rat ketamine at a low dose, so this is a sub-anesthetic dose of ketamine, the rats are hyperactive. You can see the signal, these bursts of high frequency activity. This is 130 to 180 hertz. You can see it in the raw signal, and you can see it very clearly as well in the power spectra, which is what you'd expect as well. So this result we didn't expect. We saw it by chance, and it's been about 15 years ago, and it's been something that I've been working on and trying. It's been the focus of my research for quite a long time. We did experiments in freely moving rats, so we can give the rats an injection of ketamine, we can see how they're behaving, and in parallel we can record the local field potentials. We focused on the high frequency oscillations, but of course the LFP is composed of lots of different frequency bands, and there's a lot of extra information that's there, but we focused, because we're very interested in this activity, on what happens to the power of this high frequency oscillation. So we've got 3 different doses. A low dose, the red is the power of the high frequency oscillation, the white circles are locomotor activity, and what you can see when you give an injection of ketamine, gets at this dose a small increase in locomotion and a small increase in the power of high frequency oscillations, and it's short lasting, about 5 minutes. Give a higher dose, as well you can see a much bigger increase, but what's important is that the locomotor activity post-ketamine overlaps with the power of this high frequency activity. If you give an even higher dose, which is getting closer to the anaesthetic doses, you see a biphasic effect. So you get an increase, decrease, and rebound increase. And this is basically, the rats are a little bit sedated here, so they're not hyperactive, they're ataxic in a sense. But then as soon as they recover from this phase, you get an increase in this high frequency, an increase in locomotion. So there's evidence that what the rat is doing isn't somehow related to this oscillation that we record. If you give an anaesthetic dose, this is very high, this is about 200 milligrams per kilogram, you can see there's a little bit of spontaneous activity, but anaesthesia, it's an anaesthetic dose when the rat is asleep. You lose this activity, but during the recovery, you see an increase, it reoccurs, this activity, suggesting that it is really involved in what how the rat is behaving. Because when the rat's doing nothing under anaesthesia, you just don't see it. The rat needs to be alert in a sort of a conscious state. This is what we think this means. So this just shows in more detail the baseline. This is 1 hour, basically, it's about 40 minutes post-injection, so 20 minutes before and 40 minutes post-injection. Give injection of ketamine here, you can see this very clear increase in high frequency oscillations. When you give the saline injection, nothing much happens. But what's interesting is that the delta doesn't really change. At this dose, the gamma doesn't change in this brain area, but you get the clear increase in this high frequency oscillation. If we use a different drug, MK801, which is a more selective NMDA receptor antagonist, it's more potent, and its half-life is much longer. We see a very similar pattern of activity. This is now recording up to 1 hour post-injection. You can see that we get a very similar pattern. You see this high-frequency oscillation, but you don't see marked changes in delta, you don't see marked changes in gamma, but you do see very clear changes in this high-frequency band. Because we're interested in does this have any relevance to diseases like schizophrenia? We've also examined effects of antipsychotic compounds. And these are 4 compounds that are used clinically to treat schizophrenia. So these experiments were done in mice. What we found was that when we gave clozapine, we saw quite a clear reduction in the frequency. So it slowed down this fast oscillation from about 150 hertz. It dropped the frequency down to about 80 hertz. This was dose dependent, so we gave different doses. We also looked at other drugs, as mentioned there. So these antipsychotics, in particular clozapine and risperidone, these form 2 classes of antipsychotic compound. These are atypical antipsychotics, and these are more traditional antipsychotics, sulfide and haloperidol. But we still saw this trend, even for these other drugs, for there to be a decrease in the frequency. So somehow... Yeah.
But do you know how those antipsychotics work? They affect the same receptors, or...?
The mechanisms, so they're quite dirty drugs. So sulfide and haloperidol are more dopamine antagonists. So they're D2, they have got some, I think, D3. They tend to be more selective for dopamine. But if you're talking with drugs like clozapine and risperidone, they target lots of receptors, serotonergic, histaminergic, adrenergic. They target so many different things, ion channels, lots of things, transporters, lots of things. So we tried to dissect this to see if we could use specific antagonists to try and identify which receptors were involved. We didn't have much luck. We looked at a lot of different receptors. So we don't understand why we see this. However, the fact that we see this anyways is quite interesting. The fact that antipsychotics, drugs that are used to treat schizophrenia, interact with this same frequency band that's induced by drugs that in humans produce a schizophrenia-like state. We think it's interesting, but we don't know the receptor mechanism that explains this. It's just observational at this stage. But we want to try and look at this. So I've told you a little bit about what I do. But researchers all over the world have been looking at this high frequency activity, and it's been focused on the cortex, Ventral striatum, that's mainly what we've been doing. Dorsal striatum, hippocampus, a little bit of work on amygdala, not much, but you can still see this activity in the amygdala. Subthalamic nucleus, substantia nigra. There's a lot of studies, and people are trying to understand what is producing this activity, what's it there, why is it there. A lot of the studies tend to be observational, reporting things in different brain regions. I've got a couple of what I think are quite interesting results from these studies. There's a model called the MAM model of schizophrenia. This is a neurodevelopmental model of schizophrenia. This was work done by Matt Jones's group and Keith Phillips in Bristol in the UK. They gave 3 different NMDA receptor antagonists, or ketamine, PCP you've heard of, and MK801, which I just reported on. And they studied the motor cortex. The hypothesis was that in a model of schizophrenia, these rats will be more sensitive to these drugs like ketamine, PCP, MK801. That was the hypothesis, and that's essentially what they found. It's perhaps most visible with MK and PCP, but this is a normal rat, and this is, let's say, a schizophrenic-like rat, and it responds in this high frequency band it's much more sensitive to the effects of MK801 and PCP. And that sort of fits the general idea that this high-frequency oscillation might have some relevance to models of schizophrenia. It's an interesting result. And this, as well as another study done by a group from Ireland. It just shows, again, the same sort of pattern. The pink is the high-frequency oscillation, and the other colours are the other frequency bands, and you see some increases in gamma, which is the blue, but the dominant effect, certainly after MK and pretty much after ketamine, is this pink line, which is the high frequency oscillation. And this is in a different brain region, dorsal striatum, and they showed something similar in hippocampus as well, induced hippocampus. And the big question, because all of this is done in rats, is what happens in higher organisms, like primates. Does it occur in humans? This is a really critical question. And the closest published dates that I found was an older study where this was done in primates. You could see a slight English, so it's not very clear. It's not very clear. This one, maybe you can't see, but this is the ketamine state. This is the control state. And the monkey had to perform some eye movements to focus on something. But in the ketamine state, there just seemed to be some slight increase in this high frequency activity under ketamine. There's a few, that's all I want to say on this. Because there's no published data at the moment on whether this really occurs in primates or whether it really occurs in humans. There's some evidence that some people think it does, but it still needs to be published. So I'm going to talk a little bit about, is there a primary generator of this activity? Because it's been reported in many, many brain regions, this high frequency oscillation. It's reported in lots of areas. And we focused most of our attention on the ventral striatum, on the nucleus accumbens in that area. And more recently, so this is work that I did with Miles Whittington in New York. We had did some experiments, and we had electrodes that were misplaced. They weren't in the olfactory bulb, but they were anterior. They were more frontal than where they should have been. And the target, where they ended up, was olfactory areas, not bulb, but olfactory areas. And we did various different studies to try and identify where this activity was coming from. Because in the more frontal areas, the activity got kind of progressively bigger. And so we moved right to the front of the brain, looked at the olfactory bulb, and compared it to what we had seen previously in the ventral striatum. And what we saw in the olfactory bulb was that this activity was even bigger. So this is a scale of 0.2, a scale of 0.5, and this was in the olfactory bulb. We saw something, it seems similar to what we see in the accumbens, but the magnitude is much bigger in the olfactory bulb. And so we focused a lot of our attention on the bulb. The other very curious thing is that the olfactory bulb is leaving very slightly the nucleus accumbens. So it's occurring about a fraction of, it's like 0.2, 0.3 milliseconds first in the olfactory bulb and then fractionally later in the ventral striatum. So there was some temporal difference. We also looked at muscimol infusion. Muscimol is a drug that basically turns off, it's a GABA-A agonist and it turns off neuronal activity. We had a rat, we infused one bulb with saline, we infused the other bulb with muscimol to turn off the neuronal activity, and then we gave an intraperitoneal injection of ketamine, which should increase this high frequency activity. And in the side that got the muscimol infusion, you can see there was none of this ketamine activity. This is the control side. You've got a very big increase, as you would expect. But muscimol attenuated this. That's the take-home message from this slide. You can turn off this activity just by essentially turning off the bulb. We used a little bit more advanced electrodes. So these were 32-channel electrodes. This is the bulb. This is what it looks like. You've got the granular layer. You've got the mitral layer, which is this layer. And you've got this sort of darker black area, which is the extraplexiform, which is full of interneurons and some tufted cells. And you've got the glomerulus. The glomerulus is where the olfactory nerve feeds in, and it gets projected up to the mitral cells and out to the rest of the brain. The mitral layer is very important in the olfactory bulb. And we saw reversal of phase at the point, or very close to, where the electrode crossed the mitral layer. So it's reversal of phase of this high-frequency oscillation. Again, indicating that the olfactory bulb is an important generator, involved in this activity. We also were able to record some single units in these rats, and we saw that when we got this, so this is the high-frequency oscillation, that's what it looks like, and we got some spiking, which was tended to occur at the trough of this activity. This is multi-unit activity, so you've got lots of spiking. But what's important is that when you've got this high-frequency oscillation, there's an increase at the trough of the multi-unit activity in the mitral layer. So somehow, what we think is that this oscillation, high-frequency oscillation, and the spiking of mitral cells, which are the main output of the olfactory bulb, are related. So somehow, either this oscillation regulates the spiking, or perhaps the spiking is somehow generating this activity that we record. So I'm going to come towards the end of the presentation. Can we say anything about the function of this high-frequency activity, oscillation? And I think we can. And this is basically where we are with the project today. So if we look back a little bit at some previously published work. These are homodulograms, and you can see the high-frequency activity in the cortex, caudate putamen, this is the striatum, subthalamic nucleus, substantia nigra. Everywhere you can see this high-frequency activity, and this is after, I don't know what it is, it might be after a higher dose of ketamine, it's after an NMDA receptor antagonist is being applied. And you can see that there's this high-frequency oscillation, you can see that it's being modulated by a slower frequency, around 4 Hz in this case. As well, another study has also shown something similar this is with MK801. As well, you can see this is in the hippocampus. In many brain regions, you can see this high-frequency activity, and it seems to be modulated by slower oscillation. In our work as well, we see the same thing. This is under ketamine xylazine anaesthesia. You've got these slower oscillations, and you can see bursts of this high frequency, which seem to be locked to the peaks. Recovery of ketamine anaesthesia, so this is during the recovery phase, you can see it. And in a rat, a free-moving rat, where the modulation is much faster because the rat's often sniffing, you can see as well there's some relationship with the peak. But this is just descriptive. Thanks to Jarek and Gabrisha, they looked at some of the data from the olfactory bulb, because we believe the olfactory bulb is a very important generator, and there's some evidence that there's modulation of this high frequency oscillation by slow oscillations. So we thought we need to check what happens in the bulb, because if it happens in the bulb, there can be a very good explanation for why we see this. And these are from 7 different rats. This is injection of ketamine occurring about 20 minutes after the 20-minute time point, and you can see that before injection, there's not very much. There's basically no modulation by theta. This is between, I think it's between 4 and 10 hertz. There's not very much of this before injection. You can see modulation very interestingly for high gamma. But as soon as you give the ketamine, in many of the cases you see quite robust, at least in 4 of them, perhaps 5 of them. You see quite clear modulation of this high frequency, 150 hertz activity by theta activity. When we were in York as well, there was quite an interesting experiment that sort of tends to fit this whole concept that we've got. These were rats that were anaesthetised with ketamine, and when rats are anaesthetised, they basically go to sleep. And what we found was that we didn't expect this. So this was before we got the results with Yarek. We gave rats an anaesthesia, we recorded their activity, and we could see it was gone on one side, and it was present on the other. We didn't expect this at all. And what we saw was happen when the rats were anaesthetised, where they were lying, and they were basically pushing their nostril, they were blocking their nostril. Okay? It's what we saw. And so we tried to quantify this in a more careful manner. And we did this in the anaesthetised rats just by physically using a cotton bud and a bit of plastic to occlude the nose. We can do this to occlude one nostril. When we do this in the rats, you can see as well that blocking the nostril attenuates this high frequency oscillation. You see a slight increase on the contralateral side, because when you block the nostril, the rat has to breathe more deeply to compensate. So that's why we think we see the increase there. But this was quite interesting result. We also saw a parallel reduction in other structures in the ventral striatum. So the hypothesis, we were working on the hypothesis that the theta that we see is respiration, because when you block the nostril, you block this HFO, high frequency oscillation. And so to try and look at this more carefully, we had rats that were implanted with thermocouples to record respiration in the nose, to record LFPs in the olfactory bulb, and we were trying to see whether there's any relationship, any clear relationship between nasal respiration and this fast activity. So what we've got here is, you can see maybe most clearly here, that when the rat's breathing, you can see that this is delta oscillation. This is under ketamine xylazine anesthesia when the rats are anaesthetised, so they're not, they're breathing quite slowly. Anaesthetised rats breathe about 1 to 2 hertz. Freely moving awake rats breathe much more rapidly. So you've got this delta oscillation. This is what's called a respiratory rhythm in the olfactory bulb, and this is quite well established. But what hasn't really been shown before is that this high frequency oscillation is linked as well, not only to this slower activity, but also, importantly, linked to respiration. Now, these are various other measures, but maybe we don't need to talk about them. The high frequency oscillation is slightly lower under ketamine xylazine, because under anaesthesia it drops. This is something that tends to occur with most frequency bands. When you look at anaesthesia, they tend to be slightly slower. So this is almost towards the end of the talk. We have been now looking at what happens in freely moving rats, because you can measure the behaviour, you can measure the LFP, you can measure the oscillations, and what we see is that when you occlude the nostril, you're not only blocking this respiratory rhythm, which is what we'd expect, but you're also attenuating this high frequency oscillation on the side that's blocked, and this is a longer time piece. So this is the theta frequency we talk about. And this is the average of the different rats. We've repeated it a number of times. The side that's not blocked, you see an increase in the high frequency oscillation. The side that's blocked, you don't really see this at all. We see it at a very low magnitude. So to try and tie this together, at least in terms of the rat, and then perhaps just by speculating what might happen in humans, in terms of this high frequency oscillation, we believe the olfactory bulb is very important. It's an important generator. And the mitral cells, and perhaps the tufted cells, which are cells that also are part of the bulb, important projection neurons from the bulb. They project to many different brain regions, and so possibly they can entrain or generate fast activity in other brain areas. It's one idea. Perhaps there's a clear network for how the mitral cell network can generate this activity in other brain areas, including piriform cortex, which goes on to project in the hippocampus, olfactory tubercle, which is very closely anatomically connected, or very close anatomically to the ventral, to the nucleus accumbens. Many of these brain regions are implicated in schizophrenia. In humans, the olfactory bulb is basically at the base of the, it's close to the orbitofrontal cortex. This cortical region is very important for schizophrenia. And so perhaps generating a very fast oscillation in a region that's anatomically very close might, I've read some studies through epiphaptic coupling, transmit this to closely opposed brain regions, and so might induce an abnormal change in a region that's not neuroanatomically connected with. We don't understand really what this fast activity is doing really in the rat. We've made several observations, and we're getting closer and closer, I think, to trying to identify what it might be important for. But to conclude, yeah, we think the olfactory bulb is an important source of ketamine high-frequency oscillations. Nasal respiration seems to be very important to gate and modulate high-frequency oscillations produced by ketamine and most likely other NMDA antagonists. The olfactory bulb, speculation, but it may impose high-frequency oscillations on downstream targets, including ventral stratum via the olfactory tubercle. Ketamine might disturb sensory and olfactory information processing. We haven't done these studies. We've not got evidence for this, but if you've got a very abnormal brain activity in a brain region that is critically involved in olfactory processes, you can perhaps expect there to be some abnormal olfactory behavioural change in rodents. The relevance of this activity is mainly that what we think is important is that, as I said, HFO might lead to multistructural disorganised activity through different mechanisms. And the talk's mainly focused on the abnormal or the negative effects of ketamine. Ketamine, as we mentioned at the start, is a drug that's used to treat depression, and so perhaps some of these abnormal oscillations might actually have some therapeutic benefit which we've not considered, because we've tended to focus more on the ketamine model of schizophrenia rather than the ketamine as a therapy for depression. So I'm basically at the end. People I'd like to thank very much. Daniel, who I work with, and a lot of this, the third part of this talk was done with Daniel in Daniel's lab. Władek's done a lot of the experiments, and Jacek's done a lot of the experiments. Previously, I did a lot of work with Stefan Kaszycki, who I know some of you know. But when I was in York, I did a lot of work with Miles on this, and that was a really, really good, important time, because that's when we focused on the bulb. We didn't plan to. We got results that we didn't expect, and so we had to. University of Nice, René Garcia, this is going back like 13, 14 years ago, and that was where we first observed this very fast activity. And last but not least, of course, Yara and Gabrisha, who we're working a little bit more with to try and understand how this high frequency, what's perhaps the relevance, or to what extent is there coupling between slow oscillations and the fast oscillations. So that's it really. I don't think I've got, that's it. I'm going to finish. So thank you. I don't know if there's any questions or not.
I would like to ask about these high frequency oscillations in the cortex, because schizophrenia is mainly connected, I think, with the cortical structures. So is it somehow propagating from olfactory areas, or no? Because in human, olfactory bulb is much less, I would say, important than in rodents or cats. Or
okay, that's a good question. So, in the cortex, I talk about the rat work because that's what's being published. The human work, as I say, it's a little bit of an open question as to whether or not this activity occurs in humans. You do see this. You see what you've seen here. I've focused mainly on two regions: the olfactory bulb and the ventral striatum, or the nucleus accumbens. But you do, of course, see this very fast activity in the cortex, and you see it in prefrontal cortex. You see it in areas that are classically implicated in schizophrenia. You also see it in the amygdala, to a certain extent in hippocampus. How it could be involved in the schizophrenic process in humans is a challenge to answer, because the olfactory bulb, there's some evidence that you get early changes in olfaction in schizophrenia. There's some evidence for that. There's various meta-analyses where people have looked at abnormal olfaction, and that tends to occur slightly earlier before the classical psychotic-like symptoms of schizophrenia. But it's quite possible that there's two ideas, let's say. That one is that if you get abnormal activity in the brain region, it might impose abnormal activities downstream, and the olfactory bulb can project to many, many areas. So it's possible that the seed is the bulb. There might be other regions that are generating this activity, but we have to be very careful when we say something is a generator and somewhere where you can record this. Because just because you can record it in a brain area doesn't mean that that's the site of generation. So, to answer the question, we didn't expect to see the bulb. We never studied the bulb before. We were focusing on classical brain areas: prefrontal cortex, amygdala, hippocampus, ventral striatum, caudate to a certain extent, brain areas that are implicated in schizophrenia. We didn't expect this result. And in a sense, we didn't want this result because it doesn't fit the framework of the psychosis framework. You don't expect to see this activity there. So we do see it there. And all I can say is that there's possibly these two explanations for why it could have some relevance to humans, the human condition. And that could be, as I mentioned, via the imposing abnormal activity in target brain areas, or perhaps through this epiphactic coupling, because the bulb is very close to many brain areas that are repeatedly implicated in schizophrenia, like orbitoprefrontal cortex. The key question is, does it occur in humans? That's the key question. But it's like most studies that you do in rodents or cells, whatever you study, does it really occur in humans? And that is the fundamental big question. And until we know that, it's possible that I was talking to someone, and perhaps this is rodents, and in humans there might be a very similar mechanism or a very similar network, but it's not in the olfactory bulb. It might be in the visual cortex, producing some visual or auditory cortex, producing auditory hallucinations. But I can only speculate because there's no evidence either way. Really. There's some people do MEG analysis on this, and there's an indication, but not a strong indication, that something similar happens. EEGs you can't do. You can't record this activity like EEG, because it filters below about. You can't get much above 100 hertz. It's hard to get high frequencies than that. And then as soon as you start playing around with deep brain electrodes, you really, you can't just do an experiment and give somebody ketamine. But there's some studies, some people are trying to do this in primates, which perhaps is the second best way to look at this. So yeah, that's all I can say on that, but thank you for the question.
Because talking about network in the brain, I thought about the limbic network, that it's actually, it consists amygdala, hippocampus, olfactory bulb, and olfactory cortex. So all that you mentioned, actually, that this high frequency oscillation occurred, and this limbic network, it's connected to emotional behavior of human, right, and the emotional side of feelings. And I thought, like, were possibly some research made on that, on the high frequency oscillations related to emotional, how to say, like the state of emotional higher, how to say, stimulated person. That would possibly be connected, right?
Yeah, I'm trying to think about this. There's been a lot more work done on gamma. So, because in the normal state, in rats, if we're talking about rats, you don't normally see this activity. It's very, very, very tiny. You need to give an NMDA antagonist to produce this, to get this activity. And when you give rats these sort of drugs, they tend to be hyperactive, so it's hard to do much with them. Okay? In terms of the limbic networks and emotions, I'm pretty sure there's been a lot of work done in terms of classical gamma, and during fear, I don't want to say too much because I might be giving the wrong information. But in terms of this high frequency, it's not really been looked at because it's hard to look at that in the rats that are not given these NMDA antagonists. In the normal physiological state, I think there's been work on gamma, but I don't know exactly what the outcome is for that.
So just one more question, and adrenaline, and that produce kind of the same effect of hypermobilization and hyperlocation.
Yeah.
Would be maybe also a connection, since making the sympathetic system, putting it up.
Yes.
in its working, kind of have the same results. So I'm wondering if adrenaline as a hormone and neurotransmitter as well would produce as well high frequency oscillations.
So what we've done in the past, we've given amphetamine to rats, which produces hyperactivity. We've given MK, which produces a similar sort of hyperactivity. It's hard to tell which rat's been given amphetamine, which has been given MK. When you record in the brain, you don't really see much of this fast activity in the amphetamine state, but you do see it in the MK801 state. There seems to be something. We've tried other drugs, we've tried LSD. If you give rats LSD, they don't get hyperactive, they tend to sort of remain in the same place. If you give ketamine, which normally produces hyperactivity, but you block that hyperactivity by giving a dopamine antagonist or something that will basically render the rat almost cataleptic so it can't move, you still see this activity. You still see this high frequency activity. And what we think is happening in this situation, you still see this activity because the rat is still breathing. we think there's a critical association between the breathing, the nasal respiration, and this fast activity. So before we thought it's motor, it's the brain regions that are involved in movement and basal ganglia, this sort of thing. But we think not. We think what's happening is they give the rat ketamine, inject ketamine, and then the rat is sniffing, and somehow this sniffing and hyperlocomotion are linked together. So when the rat is hyperactive, and it's also sniffing quite it's called exploratory sniffing. And so we think that there is a key link between movement after ketamine and this HFO, but this isn't necessarily muscular movement, it's called. It's rather this part of exploration in the rat sniffing.
No more questions.
If anybody's interested, I'm next door. You know Daniel, yeah? Maybe you know Daniel, or talk to Pietra, because it's very this collaboration with Jarek. I think we think in different ways. Biologists and physicists think in different ways. So yeah, okay.
So something will happen from this.
Yes.
Okay, so thank you very much.